This video is designed for GCSE computing students who want to understand what a central processing unit is and how it works, so that we can understand how all the different parts of the computer are controlled by the CPU, and we can get every last little bit of performance out of the programs that you write. So it's a brief introduction to this Battle Tanks activity that I've written to give you an opportunity to write some low-level assembly level code on a Little Man computer. So hopefully you've already had a chance to write some code in a high-level programming language like Python, and we're going to move on to writing some low-level programming code, some assembly language code for a Little Man computer processor. So the difference between high-level and low-level programming isn't that one's better than the other, or even that one's more powerful than the other. The difference is, think of it in terms of like a high-level manager who works at a Tesco superstore. The high-level manager doesn't really care what happens day to day inside the shop. As long as the shop makes money, as long as it's profitable, they're happy. Whereas a low-level shop floor operator, someone who stacks shelves, has to care exactly what happens in the shop. They have to know exactly what's on the shelves so they don't run out of any stock. And it's the same with high-level and low-level programming. If you're writing in a high-level programming language, you don't really care how your program runs, how much memory it uses or how fast it works. You just want to write some code, as little code as possible hopefully, to be able to make your program do what it's supposed to. Whereas if you're writing it in a low-level programming language, you have absolute control over how much memory your program is using. You have absolute control over how fast it's going to be. You can control the memory usage, and you have more of an idea over how long your program's going to take. So high-level programming languages are generally quicker to write, easier to understand, and you don't have to write as much code. But they tend to be more bloated, they use more memory, and they run more slowly. Low-level programs are probably harder to understand. You might have to write more to make it work, but they generally run much faster and use less memory if you write them well. So we're going to look at the Little Man computer. Little Man computer CPU was designed by some academics at Massachusetts Institution of Technology in the 60s as a way of simplifying a modern CPU. And the concepts of CPU designs, although CPUs have got much, much better obviously in the 60s, Little Man computer still works in exactly the same way as a modern CPU. So let's have a look inside a Little Man computer and how it affects us in our Battle Tanks activity. So if we have a look at Battle Tanks, you start off with a tank that you control with this kind of manual gamepad, just to be able to get used to what you can do. You move, you can shoot, you can aim, in order to collect different checkpoints and work your way through different levels. You've got different objectives, and the first one is just to be able to get used to the controls. Most of your levels, though, aren't using this manual controller. They're using a Little Man computer CPU that will control every tank that you see on your screen. So if you click on the tank, you can see the Little Man computer controller. Now, if you've done some work with Little Man computer before, you might have come across this brilliant website by Peter Higginson, which talks you through how a Little Man computer works. The idea is you've got 100 different spaces to be able to store some data. Each place in memory can store a number up to 999, and you've got 3 registers: the program counter, the instruction register, and your accumulator, which we've got here. Okay, so we've got 100 different spaces to be able to store some data, and the Little Man computer is von Neumann architecture, which means that you have both data and instructions saved in the same address space. Some Harvard architecture processors, like a PIC microcontroller that's great fun for electronics projects, will have 2 memory spaces, one for your instructions that tell a computer what to do, and another separate one for your data, where you store your variables and your numbers and all that sort of stuff. This is a von Neumann architecture, so most modern CPUs are von Neumann, so everything is stored in the same address space. So let's think about what registers are and how they compare to RAM before we go any further in looking at how this all works. So inside any computer, you've got your CPU, your central processing unit, This is controlled by billions of different transistors inside. Now, a transistor is just a switch that can control or switch on or off other parts of your processor or other parts of your computer. And all of the CPU is controlled by an electronic signal that we call the clock signal. I'm sure you'll have seen, if you research any CPU, the speed of a CPU is measured in hertz, and we call that the clock speed. So 1 hertz means that the clock signal is changing from on to off once every second. Most CPUs, the clock speed will be measured in gigahertz, which means that the clock signal will change from 1 to 0 a billion times every second. So all it means is that you switch electricity on, you switch electricity off, and you keep alternating between the two, on, off, binary 1, binary 0, electricity on, electricity off, and each time it changes, it's like someone sitting next to you in class prodding you, getting you to do something different. So the clock signal is the thing that tells your CPU to get a move on and do the next instruction in your program. So your computer needs to be able to store both data and instructions, and it can store them in your hard disk or in your RAM, primary or secondary storage. But you've also got some registers inside your processor. Remember, little man computer, you've got 3 of them to play with: your program counter, your instruction register, and your accumulator. Modern CPUs will have, I don't know, roughly kind of 60, 64 registers or more or less. They're extremely fast, but they can't store that much data. So in 1 clock tick, that means changing from on to off, you can read or write data to or from a register. If you want to read data from RAM, you have to sit around for 100 clock ticks, or approximately 100 clock ticks, which is an awful lot of time where your CPU could be doing better stuff whilst you're waiting for that data to load. Similarly, although a hard disk can store trillions of bytes worth of data, terabytes of data, it's much, much slower than a register. We're talking your CPU has to wait for 1 million-ish clock ticks before the magnetic disk will spin round to the right place for you to be able to save the data. And certainly if you're reading from a backup tape drive, we're talking trillions of clock ticks, billions of clock ticks before you can find the right data. Let's put that in context of how your brains work. A register is like a fact that you've got stored in your brain. So if your teacher asks you your name in class, hopefully in less than a second you'll be able to reel off the right information, or what room you're in, or when your next lunch break is, or simple questions that you've always got stored in your brain are like being stored in your register. If your teacher asks you to try and find out something that you did in class a week ago, 2 weeks ago, it might take a few minutes to be able to find that data in your exercise book, which is like you needing some data from RAM and you have to sit around for 100 clock ticks. If your brain can do 1 instruction per second, the equivalent is waiting a few minutes to try and get the right data from your exercise book. If you're revising everything you've ever done for a big test, it's like reading loads of data from your hard disk. And it might take you a few days to read through all of your notes, all your exercise books, all your textbooks until you find something useful. It would be amazing if you could store all of that in your brain, but I don't know about you, but I just can't do it. My brain's not capable of storing that much information. Registers are fast because they're stored on the CPU. Now, some people say, why don't we just have loads and loads of registers? Well, you can't do that because there's not enough space inside your register, inside your CPU for that. They can only store small amounts worth of data. They're very expensive compared to, per byte, they're very expensive compared to your hard disk. So there are ways around it, and this is where cache comes in. Cache is just a way of storing data closer to the CPU so that you can access it in less time. Say, for example, your teacher sends you down to the library to try and find something out, or gets you to open up a textbook at a certain page and asks you a question. There's a good chance that the next question the teacher asks is on a similar topic, and it's the same sort of thing in cache. If your CPU needs to read an instruction stored in RAM somewhere, it's going to take 100-ish clock ticks before you find the right information, the right data, sorry. But there's a good chance that the next time the CPU wants to read an instruction, it's from somewhere similar in RAM. So your CPU will get not just the data you ask for, but stuff close to it, store it in cache, so that next time you need it, if you've guessed correctly, and you're asking for something in a similar place, it's only going to take you 20 clock ticks rather than 100 clock ticks to be able to read some similar data. And you've got different types of cache. Level 1 cache is the fastest, but it doesn't store all that much. And up to level 3, level 4 cache, which stores even more, but the speed goes down. Okay, so we don't have to worry about how cache works, that just is taken care of automatically, but as long as we understand that we've got a limited number of registers and a slightly larger amount of RAM, then we can begin to be able to write some code that controls this with our little man computer. So let's look inside the tank. I'm going to reset it right to the beginning and click on the tank to be able to see some code inside. So we've already seen that we've got 100 different addresses to be able to store data. So we don't just store the value in memory, we also have an address. It's like walking down a street and seeing the number on a door. You start at the top of the street, you see house number 1, house number 2, house number 3, and then you see the people inside the house living there. So the address is like the number on the house, and the value is who lives in that house. Okay? We've also got von Neumann architecture, so we've got both the instructions and the data all stored in the same place. But let's start understanding what the registers do and how your CPU actually follows this program. So we'll restart, we'll go back to the beginning. And your CPU follows what's called the fetch, decode, execute cycle, or sometimes just the fetch, execute cycle. And we can step through that cycle here. So the first stage is fetching, and what that means is we start with our program counter register, which always starts at 0, and that means we go to address 0 and find the value stored at address 0. So the value stored at address 0 is 901, so we store that in your instruction register. So our current instruction, the thing we're currently working on, is 901. That's our fetch cycle, stage done. We then move on to decoding it, which is working out what 901 means. So 901 here, we can see is the mnemonic for that. Notice the code isn't as easy to understand as Python. It's just each instruction here is stored in a separate memory address. So 901, if we click on help, means, well, the 9 first of all means either input or output. The 1 means it's an input, and the 0 means it's slightly different to other versions of Little Man Computer, although every program you can write on here will work in the same way on your tank. We've also got some additional input and output devices. As well as displaying a number to the screen, we can find out how much ammo or how much fuel we've got left with different input devices. We're interested here in input device 0, which is just asking the user for a number. So let's have a look, we'll step through. We execute it and we're asked for a number. Let's type in, I don't know, 43. So instruction 901 asks you for a number and it stores the results, which we typed 43, into your accumulator register. So that's the fetch execute cycle done for this instruction. Let's move on. Program counter gets automatically incremented or increased by 1. So instead of being pointing to 0, we're now pointing to address 1. We fetch 308 from address 1 and save it into our instruction register. Then we decode it, we work out what 308 means. So this is our instruction set. In Python you might have thousands of different commands you can do. In Little Man Computer we've got a reduced instruction set, a very limited number of instructions we've got, only about 10 or so. So 308 means store. So we're storing, the 3 means store, and the 08 means we want to store what's currently in the accumulator register into address 8. That's this one here. So at the moment address 8 has 0. When we execute we should see 43 appearing here. Let's have a look. We execute it and good, we've stored the contents of your accumulator register into address 8. Okay, let's go through a little bit faster. Next we're now on address 2. Our program counter points to where we are in our program. We've fetched 901 into our instruction register, and if we decode it, we've come across 901 before, which means input from device 0. So let's go for, I don't know, 6 this time. Stores the result in our accumulator register, and then we move on to the next instruction. So program counter points to address 3. We grab the contents of address 3 into our instruction register. We decode it, and 308 means we want to store, so 309 means store whatever's in the accumulator register into address 9. So let's execute it, and we've got 6, which is in the accumulator register, in address 9. Okay, we're getting there. This program so far has asked us to enter 2 numbers. If you've looked at the code, excuse me, we can begin to see that hopefully our program will add the 2 numbers together and display the result. So let's have a look. Let's step through. Next, we've got 508 in address 4. 508, when we decode it, means we're loading into our accumulator what we've just put into address 8. So we're loading this value, 43, into our accumulator register. Let's execute it. Good, we've got 43. Next, we're saying 109 is our current instruction. Program counter points to address 5. So we grab the 109 into our instruction register, which means we add what's currently in our accumulator register to what's in address 9. So address 9 is 6. We've got 43 in our accumulator register, so when we add the 2 together we get 49, and that's stored in our accumulator register. Okay, we're almost there. So now we're on address 6 as our program counter. Our instruction is 902. 902 means output to device 0. The 0 in here means device 0. And when we run it, that means it's going to display our answer. So our program asked us to enter 2 numbers, it added them together, and it showed us the result. Final instruction here, at address 7, we've got 0 stored, so instruction is 0. Now, this is a special instruction which means halt and stop the processor, just so that the processor doesn't increment the program counter anymore. It stops at this address, so that we don't start executing what's stored in as data instead. Okay, so your job is to work your way through the different levels, to write the code, to be able to control your tank, to collect checkpoints, blow up mines, whatever. You can do it by changing the memory contents or by writing the code on here. So let's have a look. For this level, we want to move the tank forwards 1, 2, 3, 4 spaces. If we run it at the moment, let's have a look. We'll step through. It will just move forwards 2 spaces before it stops. So let's reset the level. So one thing we've got different here, we've just added a label. So when we've got some data down here, let's work out what this program does, and then we can understand what the labels are for. So in order to move, we need to look at our output devices. Now we've got 5 different output devices. I've already showed you output device 0, which is just display a number. Output device 1 is to be able to move forwards or backwards. Output device 2 lets you steer in any of the 4 compass directions. Output device 3 will let you aim in 8 different directions. And then you've got output device 4 to be able to shoot. So if we're moving, we've got 2 choices. We can move forwards or backwards. To move forwards, we need to make sure we've got a 0 in our accumulator register. So that's what's happening here. DAT means data. We're storing a 0 at the current memory address. So you can change this to whatever you like, and you'll see that number stored in memory. So whatever number you like can be stored here. But we want a 0, so we're going to put 0 there. Forwards just means, it's like a variable in Python. It means this memory address is memory address 4, but we're going to call it forwards, which is useful because if we ever add in any other instructions, we can still keep the same name even though the address has changed. Okay, so our program at the moment loads. It doesn't load 4 into memory. It looks up memory location 4, which is forwards, and stores that in our accumulator register. And then it will send that 0 from here to output device 1 to make it move forwards. It will do the same again to make it move forwards again. So if you want your tank to move forwards 4 times, you need to send the same value to output device 1 4 times. Okay, so hopefully you can run it. You'll see it stepping through, the program counter keeps going up, and it should complete the level. So work your way through, experiment. Of course there's ways to cheat. At any point you can change it back to manual mode if it's easier, just to be able to see what you have to do to complete the level. But it's not about cheating, it's about experimenting and finding out how you can write code, how it affects the memory, so that you can have complete control over every aspect of your processor. We're no longer relying on high-level programming code that just gets the job done but creates, bloated programs that use loads of memory and might run quite slowly. If you're able to understand how to write low-level assembler code, you know how the CPU works, you know what the registers are doing, you understand the fetch-execute cycle, so you know how each part of a computer can be controlled so that you can get the most out of your programs. Feel free to explore. Battle Tanks is in its very early stages of development. I've only cobbled it together over the last couple of weeks. I've tried to put some help on this wiki on here if you need any more help or resources. If you have any ideas or want to extend it or make new levels for it, by all means do. The whole project is open source, so you can download the code, tweak it and change it, add your own levels and make it your own. I hope it's useful. Feel free to play around and let me know if you use it for anything useful. Thanks a lot.